on using anonymizers and still getting fucked. Have fun.
So, thanks for coming to this talk. This is Lexi. I am Dominic. Lexi is working at IDEF. I am working at University of Regensburg. And we're going to talk about 4 different topics related to profiling of web users in presence of anonymization services. So first part is Lexi's part.
There's one major subline on the whole talk, and that is provided that you are using some kind of IP layer anonymization service like a single hop web proxy, Tor, whatever, choose it, you are not just safe automatically. And we'll show several examples in this talk that still can do some harm to you. The first part is filtering of JavaScript in web-based proxies. So web-based proxies are something like PHP scripts proxying HTTP requests. You have seen those most likely. And we have taken a look at 2 of the more popular implementations. Unfortunately, both of them are kind of dead pigs, so hacking them is really not so much fun. Still, they are out there and they are widely used. So just in case you come across one of those, be very cautious. If you look at the code, it feels a little bit like Rocky training, so just beating on a dead pile of meat. The first thing is actually, well, why don't you want to have JavaScript in your browser? Because JavaScript is a Turing-complete language. You can do a lot of stuff with it, and especially you can profile users in a lot of ways. Like, I'll skip those details, but I just give them orally because you already know it. You can grab the screen size of the user and profile him. You can get the time zone of the user. You can get the clock drift from the user, like if his clock is permanently 5 minutes late, you can use that to identify the user. And there are many more examples. So basically you don't want to have JavaScript running in case you want to be anonymous. Now, phproxy does use regular expressions to filter out JavaScript. The problem is that HTML is a language that is way more capable than regular expressions. If you have ever visited a second-year computer science class, then you probably know that regular expressions are just regular automata. But in order to pass HTML, you need something like stack machines. So this goes wrong in just another way, and I will not go into that in many more detail. I'll just show you that first what phproxy does is it removes all the script tags, and after he is finished, he removes the no script tags. Why he does it, I don't know, because if you just use this way, then phproxy will, well, actually it will just remove only the no-script part, and then you got all the no-script, the JavaScript through the web-based proxy. And then you can again use all this JavaScript to profile the user. Okay. So the use case for this one is a user has no script enabled, but it just has enabled JavaScript from the original web page, but not from any other web page. So what you can still do in JavaScript is you can just load a CSS from another server, and usually the loading of CSS is not filtered in any kind of web-based proxy. So you can use this one also to just identify the real IP of the user. And finally, some proxies do filter JavaScript applets, Java applets or Flash applets, but they just filter here the original path up there. What the what the coders of those proxies did not knew that if you put the path a second time down here in the param tags, this one gets completely ignored. So while they filter that one, this one is actually getting used. So it makes no sense to filter that one. So that was the first part.
Thanks, Lexi. And the second part is on identifying users based upon their web profile. So all of you are aware of the problem web profiling may cause to users' privacy. What I am talking about is if attackers are able to observe a user's web requests over a long time, they may learn the user's interests and even maybe their identity. Remember the AOL search log thing when AOL released search logs when some of the users contained in these anonymized log files could be de-anonymized solely based on their search keywords. Now, we're considering specific attackers in this talk only, and the attackers we are considering are either anonymizing proxies, like web proxies or CGI proxies. We are also considering third-party DNS servers, like the popular Google Public DNS, which is pretty fast and says it's secure, and OpenDNS. And we are somewhat also considering anonymizers like Tor, but only very briefly. And the overall question is whether we can whether those adversaries can track your activities if you're using them. So if you're using anonymizer.com daily, can anonymizer.com track you over several days? That's the central question here. Obviously, this is rather trivial if you're always using the same static IP address. If you're always using Anonymizer from the same address, Anonymizer just has to basically union all your web requests and build a big, large, fat profile out of them. And until now, most people would think that it's rather difficult if you're not using the same IP address every time. So if your identifier changes frequently. And now you would say, fortunately, I'm using a DSL provider who assigns me a new IP address every day, and fortunately, Tor switches circuits every 10 minutes. But what would be if we could actually link multiple sessions and basically tie them together, match them together, solely based on your surfing profile? Then we probably would get into problems here, right? So let's assume this scenario. We started out assuming that user behavior as it is reflected by the visited destination host names, so the sites you're basically going to. And the situation is like depicted in the graph here on the left side. You got two users, user 1 and 2, from two distinct IP addresses, and those two users are visiting different hosts. They are basically surfing to different hosts. At a later time, you're observing two other IP addresses, IP 3 and 4, and the attacker questions now, is user 1 session 3 or is user 2 session 3, or is user 1 session 4 or user 2 session 4, or is it someone else, someone totally different? Fortunately, we don't have to do this manually, but we can use data mining techniques here. And using data mining techniques allows us to treat the session linkage problem as a classification problem, like a standard machine learning task. And what we're doing, we're feeding a classifier the earlier sessions, like session 1 and 2, training it with it, and then we're asking the classifier what it would predict session 3 is the matching user's profile. And then the classifier might hopefully say that session 3 looks very similar to session 2, and therefore both of them belong to user 2. The question is, which classifier should we take here? And this is a problem of its own, obviously, for those who are familiar with machine learning at least. And we observed that the total host access frequencies, so the number a host name is accessed by a large population of users, resemble closely the word access or the word frequencies in natural language. So on the left side, you see the distribution of words in the Bible. On the right side, you see the distribution of hosts if you have a large user base, like here on CCC. And those are obviously similar. And that's why we started out to tackle the problem with the same techniques as are applied in the text mining domain. In the text mining domain, we are talking about instances, about documents. And the document consists of terms, of words. And in our setting, the words are actually host names. So what we can do is we can use the instances, or we can construct instances by just adding the host names that are visited in a user session on a given day. And we don't have to do it ourselves, but we can use standard text mining tools like the Weka package, which is a Java machine learning package. And we just use all the tools Weka contains for text mining, like the string-to-word vector filter. The filter reduces weights and tunes the vectors in a way so that bad things are not happening and certain characteristics are removed. And then we can use the so-called multinomial naive Bayes classifier in order to classify texts or hosts or sessions. And fortunately, I'm not going to talk about the intricacies of this formula here, but I just tell you that the basic idea is that the more often you're observing a host in a session by a given user, the more likely it is a session that belongs to the user if the user has accessed this host in the past, which makes total sense. So if you're going daily to slashdot.com and the attacker observes you going to slashdot.com, he argues, well, that's probably the same user. Obviously, Slashdot is a very bad example. In order to evaluate this hypothesis, whether this would work, we carried out a small study with 28 volunteers who volunteered their traffic, 57 days in total, to us. And obviously, it's not very easy to find such volunteers, especially if they're volunteering their traffic to interested researchers. So we had to think about privacy here. And what we did is we recorded all the traffic at their site on their local machine with a proxy, Privoxy actually, and obfuscated all the host names in the log file with a salted hash function, so that we ourselves would not be able to find out which host names they were looking at. We were only seeing hash values actually. And all participants uploaded their log files via an anonymizer, so that we really don't know who uploaded what. The scenario is basically like this. The attacker wants to track on day T some specific user. He trains a classifier with all users that are present on that day. On the day T+1, next day, following day, he is confronted with different IP addresses, different sessions, and now he asks the classifier to predict what the mapping between sessions in day T and sessions in day T+1 is. And we, as researchers, we can actually evaluate this because we know the true mapping, we know the true identity, at least we know the true pseudonyms of the users, although we don't know their identities. And repeat for all days and sessions. The results are rather intimidating. All 28 users had some characteristics, and we could actually link 77% of consecutive sessions. So from one day to another, if you were using the same service, in 77% of times, those two sessions would have been linked. There was one especially poor guy in the study. We could link 39 out of 57 days, using only host names. Now, while this is certainly interesting and maybe even a problem, we wanted to know whether what the actual characteristics of this problem are. So what we did is we looked at different session times. So far, I only looked at day, meaning 24-hour session times, and you see this is the peak with 1,440 minutes in this graph. But what's also interesting is that when you're doing really short session times, like 10 minutes or 5 minutes, remember Tor's 10-minute circuit switch time here, you see that the accuracy actually goes up again, which totally makes sense, because when you're surfing on Slashdot, you might do that for 5 minutes, for 10 minutes, and if you happen to be the only guy doing that, then your sessions, your consecutive sessions, can be linked easily. Now, for consecutive sessions, this is probably not so difficult, but what happens if the offset between training the classifier and testing the classifier goes up? So that's what is depicted in this graph, and what you see First is that for rather short sessions of 1 and 3 hours, the accuracies drop only slightly if you're basically having an offset of up to 7 days, which is at the right side of the graph. And what is also interesting is that there are daily regularities. So every 24 hours, the accuracy slightly increases, which is probably due to that all of us are doing the same things during the same time of day. So you're doing the same stuff in the evening, but different stuff in the morning. Same stuff in the night, different stuff during the day. Now, this is certainly not so interesting doing it with 28 users only. And that's why we repeated the study with a larger body of 3,100 users, having 11 days of DNS logs of a big university. And the results are intimidating again. Accuracy is still at 70% overall. And what you can see in the graph here is that 80% of the users could be tracked on consecutive days at least 50% of the time. So what would we recommend if you feel that this is a problem and you want to protect yourself against that? First, change your IP address frequently, if possible. Second, if you can change the IP address, do not do the same stuff which you did before you changed it, because otherwise the change is useless, obviously. Or if that's not an option, you might use different proxy servers, different DNS servers for different activities, like all your Slashdot stuff on this proxy server, all your Facebook stuff on a different proxy server. What doesn't really help is randomly splitting your requests to various servers. We tried that out. We simulated 50 proxy servers or DNS servers and randomly splitted or randomly distributed the requests of the users, and accuracy is only decreasing slightly from 77 to 54%. What's also not really an option is to restrain yourself and restrict yourself only to the top most popular pages, because we thought that it's probably a good idea to only stay on Google and Facebook and Slashdot, because that's everyone doing, right? But that's not really helping. 1%, which equals 250 hosts in our sample, still reached an accuracy of 66% for daily sessions. So obviously there's research to be done here, and that's an interesting problem we wanted to share with you. So next up is Lexi again.
Yeah. So the next chapter is about detection of bots, or in general strange users of a web page. Why would you want to do that? The problem is when you run a corporation web page that is something big, the problem is that sometimes bots really are a pain in the ass because they fetch all pages non-stop. On some servers which I maintain, there are sometimes bots who fetch the complete web page every 2 seconds. This just induces heavy load. There are also bots who ignore the robot's text, which is there for a reason, so they descend into some kind of structure where you don't want to have them. And the other problem sometimes is you just have proprietary information and you don't want to have your database crawled by competitors. So one way or the other, you don't want to have these bots on your web page, so what are you going to do? The most simple thing is, obviously, if you have load balancing, you can just use some kind of deterministic way to redirect all the users to the single servers. Like what you could do is you just prepend some salt to the IP, make the MD5 sum, convert it into an integer, modulo the numbers to the servers, and then you redirect the user there. Then what you can do on the single subserver is just you check the original IP of the user, check if it should be there, and if it actually would belong to another server, you can just drop that user as being a robot. The fun thing is that even if you think this is too trivial, I could show you actually logs from the servers where the log file from the server 0 has 10 times the size of the server from number 7. That's mostly because all the bot users out there just stick with the lazy option and always use server 0 instead of the one that they actually get redirected to. So this already helps. The next thing is, I've never seen a bot anytime loading some kind of JavaScript or images. So you just check your log files. All the users who do not load a realistic share of these kinds of images, just drop them. I'll get to that in a second. And the other thing is that humans usually don't reload files on and on like every second. So again, counting just the number of hits a user makes on your web server, just drop them. Getting to the realistic share, in case you really want to try that out, this one works for me. Actually, what I do is I do not have an absolute level of evilness. Where I drop the users, I just take the top 1% quantile and just kick them. So getting into fake user agents. A lot of bots actually fake user agents. I mean, anyway, if you want to get proprietary information, you would never put a user agent there that says something like, hello, I'm your competitor, please give me all your information. So first things first, a lot of these people use Internet Explorer 5.5 or something randomly, something which is really seldom seen on a real computer nowadays still. You can just put a static website there displaying them to just upgrade their bot. The next thing is that actually there are many more HTTP headers out there than just the user agent. So why not use that one? And the funny thing is that any HTTP header out there in a different browser, they're uniquely ordered. So what you just go there, I'll come there in a second, take a list of all the HTTP headers in the request, and take a look at the order of the request, and then you can see what the browser actually is. What you would do then is compare that to the user agent and check if the user agent tells the truth. If the user agent is forked, well, kick him. One technical remark here, coming from the intrusion detection system guys. Usually, what you can run into here is there are lots of intrusion detection system evasion techniques, like making a TCP connection and then just sending the request byte by byte, so that if you just take a look at the single byte stream, you will have to reassemble all the byte streams. If you want to avoid that and just want to have a convenient life, anyway, as I said, you most likely have a server farm and a load balancing proxy in front. Just take the data from behind the load balancing proxy. The HTTP stream will readily be assembled, and there's no need to go through all the IDS evasion techniques yourself. So now let's take a look. Here I got the Firefox and the Internet Explorer. And what you can see is that while cookie is the last one, for example, Firefox sets the host header first and the Internet Explorer last. Opera puts host somewhere in the middle. Chrome cookie is not last. And then there's several Symbian browsers. You can ask Colin about them. And then there's these notorious, what you see sooner or later, wget or all the Perl things. Already from the number of HTTP headers, you can tell that wget or the Perl libraries are definitely not real browsers. And the funny thing is that you can even distinguish wget and Perl. And if all these things are a little bit too complicated, I got it more visual here for you. So same colors are same HTTP headers. The black one is host, the red one is user agent. This is already quite unique. I left out a few quite single ones, and they are still white. So what you can see is that we don't need the user agent. We just take a look at all the HTTP headers. We know what your browser is. If you spoof the user agent, thanks, goodbye. So basically what I wanted to say is that if you use another browser, be frank about it and don't try to fake it, because sooner or later we'll find out. So next one is Dominic again.
Thanks, Lexi. So, final and last part of this talk is regarding local attacks on Tor, and you will see what's about that. Now, Tor, I guess we are not going to explain it to you again. It's a mixed network, if you haven't heard about it. And the interesting thing is that in Tor, local attacks, like attacking the connection between Alice and the first entry node, or the entry node, are supposed to be not possible, right? Because everything's encrypted 3 times, and rather difficult to find out what's transferred from Alice to the entry node. So Tor support is supposed to protect us against local attackers. That's why many people are using it when they are in a foreign network in order to protect their privacy. Now, we're going to show you an attack which might question this statement. And the attack is basically called a website fingerprinting attack. This is nothing new. It has been researched since at least 2002 in various things and various procedures. And we're only working to improve it slightly, and even more slightly. The basic idea is that website fingerprinting is a traffic analysis attack, and all traffic analysis attacks are operating on metadata only, meaning they're not relying on content whatsoever, but are taking timing, packet count, packet sizes, direction, and stuff like that into account. Only that, nothing else. And it's pretty easy to see that most websites are unique in terms of size of images, number of images loaded in different ways. And so if I would give you the sizes and counts of images, you would probably be able to identify a website just from that. So if you knew the HTML file is 50 kilobytes and there are 10 images with sizes A, B, C, D, and so on, for many pages this is a unique fingerprint. Unfortunately, this unique fingerprint cannot be easily seen if it's transferred over Tor, because the browser uses pipelining and multiple parallel connections and such stuff, which makes it really difficult to see the actual image sizes. So what we're seeing is packets, direction, timing, nothing else. And it's really difficult to go from file sizes to packets, as we will see. The basic scenario is, as I said, you have an attacker which is eavesdropping on your local connection somewhere in the Wi-Fi hotspot or your ISP, your admin, whatever. And the attacker has a list of interesting sites, interesting for him. Those are the sites he would like to know when you're downloading them over Tor. Well, in theory, this shouldn't be an issue because Tor uses fixed size cells, 512 bytes, padded if there's not enough data, and in theory, everything should be fine, right? Let's say everything's fine, but continue with the talk anyway. There are 2 stages to a website fingerprinting attack, and the first stage is preparation, where the attacker basically downloads all the interesting sites he's interested in, meaning he wants to identify at a later stage. He uses Tor himself, and he downloads them multiple times, like 20 times in the course of a week. That's what we're calling training data. And already now you can see that this is going in the same direction as last time, as last part of me, we're going to classify stuff. Second part of the preparation phase is eavesdropping on the victim, which is supposed to be easy in this talk. We're not talking about how to do that. And this will be the test data for the classifier. And then the attacker goes down into a cellar and basically classifies, does statistical analysis. What he has to do is he has to extract fingerprints from the training data. I will get to that in a minute. Train the classifier with those fingerprints. Then he will basically apply the classifier to the test traffic, and the classifier will tell the attacker which site might have been retrieved. There's a number of assumptions here. I have not put any details about them on the slides. I can tell them orally in short. First assumption, the attacker knows which operating system the victim is using, which browser the victim is using, so that he can replicate the victim's traffic realistically and pretty well. That's probably not too bad assumption because there are not so many operating systems and not so many browsers. In the worst case, the attacker tries all combinations and the right one will be there. Second assumption is definitely a harder assumption. The attacker is supposed to be able to extract single web requests, like the download of a single website from the stream of data. It has been shown that this is a hard problem because most users are doing multiple stuff at the same time. There may be web radio in the background and all sorts of stuff. But for now, we're ignoring this problem and we believe that the attacker will have somehow the capability to extract single page loads. Yeah, so that's that basically. Now, what does this website fingerprint look like? And keep in mind what I was talking about when I was talking about instances in the second part of this talk. We're starting with the output of a TCP dump this time. In a TCP dump, you get easy access to the packet lengths, direction of flow, and timing. But what we're actually only interested in the very basic case is packet lengths. So in this case, you got them printed on the slide, and the target or the aim of the attack is now using those packet sizes, solely those packet sizes, finding out whether it's website A, B, C, or D. In order to give you a visual impression of what those fingerprints are looking like, they look like this in a histogram form. So on the x-axis, there are the packet sizes. Left-hand side is all packets sent by the client. Right-hand side, all packets received by the client. And you got the frequency in the y-axis. So obviously, this is pretty similar to the former problem with host names and such stuff. So we can use similar techniques, right? We applied two classifiers. The first one I have talked about already, multinomial naive Bayes. And the second one are famous support vector machines, basically the state-of-the-art classification engine used by machine learning people today. I cannot explain to you how support vector machines are working. Let's say they work magically. It works, definitely. There's something about hyperplanes separating instances, and no, you don't want to hear about that today. An important part of machine learning in general is feature extraction. And so far I've only talked about extracting the packet sizes, and this works not really well, at least not for Tor. For Tor, colleagues of mine actually found that you have to have other features in order to get more discriminating features. And these are direction markers and dropping acknowledgement packets. So you drop all the acknowledgement packets, and what's remaining is basically accumulated as long as the stream flows in one direction. So if you got 5 packets downloaded by the client, you sum them up, you sum the sizes up, and that's your new packet size. So you aggregate it. So order of flow is relevant now. We set up an experiment in order to evaluate this again. 775 popular sites downloaded via Tor in the real network, 20 times per site. And we evaluated it using tenfold cross-validation, which for all the guys who don't know about machine learning theory, in one sentence, it's a method to make sure that you do not choose, or that your examples or that your results are not due to randomness, but they are basically validated because you repeat the experiment 10 times with 10 different samples. So we started out in 2009 with that, and for single hop proxies like OpenSSH tunnels, OpenVPN, and so on, this works really well. Like 95% of those 775 websites could be identified. For Tor, it didn't work too well. It was like 3%, not to talk about actually. For the YAP or John Donum anonymizer, it was not too bad, like 20%, already a risk maybe. But our colleague Andrei Panchenko, who actually graduated from his PhD recently, found some nice improvements which are more concerning. Now he is able to do it for Tor with up to 55% in the real network, for YAP up to 80%, and in the local Tor network he is up to 89% of accuracy now. So this is certainly bad because it's getting feasible now. And if you're looking at YAP, especially because I know that there are some YAP guys around here. So on the left side you see the Tor data, and those bars are basically the different classification methods. Tor is worst. The free cascade, the Dresden cascade, is slightly better, meaning slightly higher accuracy. And actually the premium cascade, which is supposed to be more secure, has an even higher accuracy, meaning bad for the user. And the private network, for reference only here, has basically the same accuracy as the premium cascade. So even though YAP uses bigger packets, 998 bytes per packet, it's performing worse than Tor regarding this attack. That's pretty bad news if you thought that packet sizes and padding helps protect your privacy. In fact, fewer packet sizes don't guarantee protection at all. If you're looking at those accumulated graphs here, you see basically all the packet sizes that occurred during the tests. You see that the free cascade, which is located only on one server, has very few packet sizes. You can count them on two hands probably. The premium cascade has a lot more packet sizes, and the real Tor network has really many packet sizes. And that's due to TCP fragmentation, basically, which is happening all the time in the Tor network because it's overloaded, so slow, different operating systems, and so on. So there's no guarantee regarding Tor's 512 byte cells. What I was talking about so far, beautiful, isn't it? Right? If you haven't been there today. What I was talking about so far was everything was under the closed world assumption, meaning the classifier was only presented websites it had been trained beforehand. So the classifier was always trained with 775 pages, and then it had to classify 775 different traffic samples. That's not really realistic, right? Because in the real world you got billions of pages, and only a very few of them are interesting. So that's why we left the closed world and put it into an open problem. And that's done by using a very few number of interesting sites, like 5. If you're like a law enforcement agency and you want to find out who is doing stuff on your network or in your country that's maybe forbidden because of religious reasons, that's a good cause for using website fingerprinting, from their point of view at least. And they would put basically a blacklist of pages with sexually explicit content on the network at the ISP level, and would try to find the people who are downloading that stuff, which is, from a religious perspective, not allowed in their network. What they would do is they would put a lot of random sites into one class, we call it the other class, in order to lure the classifier away from classifying uninteresting pages to those sexually explicit pages. So we need a basin where the classifier can basically put all the randomness of the internet into. The following experiment uses 5 interesting pages, samples uninteresting pages from the Alexa top 1 million list, and the question is, how many uninteresting pages should you use during classification to get less than 1% false positives? That's an important thing, to get only few false positives, because each and every time you get a false positive, you think someone retrieved sexually explicit content, although they didn't. And the graph looks like this. The answer to the question is you should use 2,000 uninteresting training instances in order to get a low false positive rate, and the true positive rate stays at 67%, which is still pretty bad from privacy research standpoint. So what should you do? And padding is obviously not so easy, but what's really easy to do at home, do multiple things at the same time. Use 2 tabs, use a web radio, use whatever you're doing that causes network load while you're doing stuff you would not like to see others. In experiments, this decreased rates down to at least 10%. So if you're doing that constantly, this attack is no issue for you. So that's basically all of what we would like to share with you today. And at this stage, we definitely have to thank Rolf Wendolski from Jondos, who contributed the first part, if I remember.
The JavaScript stuff.
And we definitely have to thank Andrei Panchenko, who contributed much of the fingerprinting stuff. And Lexi wanted to make a statement about IDEF. Are they hiring? I heard about that.
Yeah,
no.
Could be. Well, I think we're done. We
Yep.
take questions.
So, hands up if there are questions.
On? Okay. I have a question about the classifying of the sex types. What kind of features did you use for your classifier?
Packet sizes, nothing else. And direction. Yeah, packet sizes and direction. No content whatsoever. So you need to have a list. You need to have the list of sex pages you're interested in as attacker. So no image recognition stuff.
Hello. Test data? Is it possible to download it?
Excuse me?
He's asking about test data. So you want to download test data, traffic data, basically. I can answer for myself that I have put on my website at University of Regensburg 2 gigabytes worth of traffic logs. They're old. They're from 2008. I'm not sure whether Andrei is releasing his data. Probably.
I don't know.
We should ask him, or you could contact us.
Send us a mail and we'll see what we can do.
I have a question about the header order. How accurate is the header
Excuse
order?
me? Could you?
Speak up, please.
Yes, sorry. The order of headers in the browser.
Yeah.
The browser sent. How high is the false positive rate on fingerprinting with using that?
Well, the big point is measuring false positive rate. If you assume that we measure false positive rates by customer complaints, then up to now it's 0.
Okay. Thank you.
I want to know how static the fingerprint of a website you're making is, because I'm thinking about pages like 4chan or things. They change quickly enough that a text doesn't seem viable for pages like that. Just wanted to know if there's mitigation of that or stuff.
Yep, so you're asking about whether it makes a difference, whether the page content changes, whether that makes a difference. First, in our experiments, the rates didn't decline much if the offset between training and test were like 2 weeks. So that makes almost no difference. And it's easy to explain because it doesn't make a difference if the text, if the contents change. It makes only a difference if the structure changes. So 4chan especially might be tricky due to its nature, but news pages, sexually explicit pages probably work pretty well.
But then again, nothing stops you from retraining your classifiers every half an hour.
Question from IRC. Is it difficult to fingerprint websites which change very frequently?
I think we got that already covered just right now.
Internet never disappoints.
How does caching affect the fingerprinting?
Sorry, how does what?
Caching.
Did you get it?
Caching?
Browser caching.
Caching, oh yeah. I did actually experiment on that, not with Tor, but with OpenSSH, and it's decreasing rates from 98 to 92 or something like that. So I cleared the browser cache and I didn't clear it, and that's where basically the difference came from. So it's not so bad, because most browsers still at least query whether the object has changed, which means an HTTP request in the response. So you definitely get packets even if nothing has changed, because the browser usually can't decide on its own that nothing has changed, but has to look it up on the web server. At least a not modified answer has to come back. If it's not coming back, meaning if you're basically mirroring the whole internet, then you're definitely safe.
Oh yeah, and then just think of caching, that if you've got a browser like Chrome in incognito mode, then usually if you do something privacy sensitive, you don't cache at all typically, so because you don't want to have this stuff on your local hard disk.
So, wouldn't heavily personalized page like Facebook
Could
Stream...
you wait for something? Okay.
Wouldn't personalized, like Twitter Stream, Facebook, prevent you firstly to fingerprint the page and give me privacy?
So you mean, I'm not sure whether I got it right, but what I understood is whether a personalized page is immune to fingerprinting.
Yes.
No, it's not, because the structure is basically the same. If your Twitter page lists 20 items, it will always list 20 items. I mean, the text doesn't matter anyway, it's encrypted, right? So as long as you don't have a personalized page which is very different each and every time you download it, which I don't know about actually, then you're not safe.
This, from a statistical point of view, this was a first order analysis. Are there any efforts to do a second or higher order analysis to have time correlations between packet sizes? I think this should increase or decrease the safety dramatically.
Timing is a problem, because timing is highly unreliable on an anonymizing network. Like on Tor, you have no timing guarantees. Each and every time you download a page, it may come down over a different circuit, which is why every time you wait, but you wait differently long. So we haven't looked at timing so far, and I don't think it will help much. Actually, it might decrease accuracies. But there are definitely more features out there, and the search for better features will definitely continue. You can bet on that there are more researchers in the world looking at that problem, trying to find better features in a higher order, definitely.
Can I disable the fingerprint if I random load images that are shown on the page, or JavaScript is not?
So you wanna, so you're asking whether it's possible to download, like regularly in a short intervals, images of random size in the background.
Yeah.
That will help, definitely.
To a certain extent, one should admit. Because once you start doing that and it's really regular, the attacker can filter that out again. So you want to do that at random intervals with random sizes and random images. Like you could start a web crawler at your computer or something.
Basically, it will decrease maybe the rate of sites recognized, but may increase your visibility, right?
Yeah. If that's the thing you want to hide, yeah. Okay.
You talked about recognizing robots because they're not loading JavaScript, for example. Do you get false positives if somebody is using, for example, the Firefox extension NoScript?
No, because these people use they load images, and then what I do is I do not use all of these measures I told about strictly, but I use them for a scoring system. So if there's only one or few things that don't hit, I don't classify the users as bots.
Do you see any better ways to protect ourselves? I mean, as you know, that statistics probably will kill the loading in background thing, and yeah, well, that's not very good.
Yeah, so you're asking whether there's a
do you have any
solution?
idea for better protection? I mean, or yeah.
Apart from
idea?
No, you're asking for better protections. Well, From a network point of view, the Tor guys are probably worried a little bit only because it's not really so practical. I mean, it's only 60%. But what I'm not sure. I guess
60% is quite.
Yeah, I guess we will talk to Tor guys, or Tor guys will probably talk to us. But I'm not sure whether it's probably an arms race, right? Someone finds a better protection, someone finds a better statistical attack. So that's like antivirus or something. And I'm pretty sure that padding whatsoever will not really help. It might help, but it's really, really costly. I mean, if you pad each and every packet to full size, like 1500 bytes MTU, then you're safe, sure. I mean, but then you have to send, even if you're not sending, I'm talking about dummy traffic, meaning you're always sending with the full capacity of your line. And that's probably not something we would like to do.
It should be added that in the area of anonymous communication research, dummy traffic has been researched like the last 20 years and it never proved a final solution.
Okay, in your YouPorn example, how does it distinguish from YouTube? It's video at all and...
Well, that's the good thing about it. It can distinguish between it. I don't know. It works.
It's machine learning.
That's actually the bad thing about machine learning. You usually really cannot explain why it's working, but you can see that it is working. That's why there's this, and then magic happens slide. So obviously it's different in its nature. I mean, it wouldn't be able to distinguish if people started to upload sexually explicit content to YouTube, because it's all about structure and sizes. But as long as those two pages look differently, you can be pretty sure that they will look differently on the wire in Tor as well. So,
would you recommend combining your bot detection techniques with CAPTCHAs, or are they good by themselves?
We don't want to hassle our customers with CAPTCHAs, they suck.
I agree.
For Tor, enabling bridging or exiting relay, how does that affect?
Sorry, I didn't get it. Bridging or
exit relay?
Meaning on your own machine?
Yes.
Sounds like a good idea to me, because then you're basically having traffic which is not your own traffic. And this will definitely make it more difficult to pick out the packets that are your packets for the attacker. But are you really considering running this on your machine? I'm not sure.
Well,
one more question.
Last question, then.
What about fingerprinting on HTTPS, considering session keys have short lifetime? Question from IRC.
So what are you hinting at? Fingerprinting on HTTPS and short session keys lifetime?
Yeah, that's the question from IRC. So they asked me to relay it. But I think it was more a question asked in context, but that got lost. So if you don't understand,
I didn't get the question, but HTTPS is, if you're using Tor, no one sees what you're doing inside Tor. So if that's the attacker model, then it doesn't matter whether you're using HTTPS.
Basically, HTTPS is no protection against fingerprinting because we don't use the content anyway. If that answers the question.
Well, if there are more questions, maybe you can ask them yourselves. Thank you, Lexi and Dominic.
Thank you.
Yeah.